I'd like to introduce Esther and Travis. We're going to be talking about Unicode and character encoding this morning.
Hello, PyCon. I'm Travis. This is Esther. We're very excited to be with you this morning. I dreamt last night that we couldn't figure out how to get those slides up, so I'm feeling really good about PyCon so far. Esther and I have worked at cars.com, newcars.com together for the last couple of years. Python shop, PyCon sponsor, users of Pyramid. Esther's still with the great team at cars.com. I'm with another Los Angeles Python shop, shift.com. So I want to introduce you to Cody. Cody's experiencing pain. He's experiencing frustration, confusion. So why is Cody experiencing these things? Well, he's dealing with the heartbleed bug on his website, but on top of that, he's trying to write software that deals with character encoding and Unicode. And if you are anything like Esther, myself, or Cody, it brings about these emotions when you're trying to write software that deals with character encoding. And it may result in this, the legendary double table flip. So we're hoping this talk will help alleviate some of that pain for you.
Speaking of flipping tables, we have a confession to make. We chose the title of our talk not just because it is sort of silly and fun, but because we're evil, as the PyCon program committee found out when our talk title crashed the IRC bot that they use when they review proposals. We really drove home the point that this is a topic that's very relevant to anyone who's ever had to deal with text, character encoding, and Unicode, which is all of us at some point in our careers. Before continuing, I have to mention that we're not going to talk about Python 3 in our talk. We do want to cover the fundamentals of text, character encoding, Unicode, and strings so that you can understand at a fundamental level how those things work. And that will make it easier for you to understand the differences between the way Python 3 and Python 2 handle text and character encoding. But we just don't have time to talk about this today.
So we're going to start off with the fundamentals. And I'm going to mention Ned Batchelder gave a fantastic talk, PyCon 2012, on the fundamentals of Unicode and character encoding. It helped Esther and I understand it a lot. So I recommend go check that talk out, the video, as soon as you can if you haven't seen it. We're going to try and build on that and take you a little further. So fundamentals. Humans use text to communicate, right? We use written language, we use characters. But computers speak bytes. Computers, on a fundamental level, just deal with binary. So how do we deal with that? Well, we as programmers need to translate our written text into binary. We use something called character encoding. You guys know this, right? We take a character, like the lowercase Latin A, and we just map it to some binary representation. We assign it some bits. This is the ASCII encoding for the lowercase a. So there's a bunch of different character encodings out there. They're all unique. They do things differently. They do try to agree and have some compatibility for like your basic A to Z set that's represented in ASCII. But because they're unique encodings, they differ. A character like the euro symbol is represented with different binary representations in these various encodings. And the result of that is that the same binary sequence may represent two different characters depending on what encoding you are using. And this is the cause of a lot of pain.
Let's think about all the characters that we like to use in our written communication that don't lie under, that don't fall under the standard A to Z 0 to 9 range that ASCII presents us. We like to use mathematical symbols, punctuation marks, and even Unicode snowmen. And of course, there are other languages in English that have their own scripts. Some of them have dozens or even hundreds of characters that also need to be encoded. So Unicode was a way to standardize the way that we can encode any character that anyone might ever want to encode. The way Unicode does this is by providing a universally recognized mapping between a character and a Unicode code point. This is a universally recognized identifier for a character. It's denoted by a capital U and a plus sign, followed by a unique hexadecimal value that's assigned uniquely to that character. What you should note is that Unicode does not provide a binary mapping for a character. Code points are purely an abstraction layer. It's limited to the character itself. It's wholly separate from any binary representation. It's purely a description for a character. Of course, ultimately, computers do need bytes to deal with text and transmit it and store it. So what we need is a way to map between a Unicode code point for every character to that binary representation. So what we need is a Unicode-aware encoding, a Unicode transformation format, or a UTF, of which there are several. But the one that you should use wherever you can is UTF-8. For many reasons, it's become the de facto standard used across the internet, used by email clients, internet browsers, and operating systems.
So Esther just explained Unicode and UTF-8, right? These are highly related terms, but I just want to drive home the point. They are unique ideas, and you shouldn't just blindly use those terms interchangeably. Unicode is code points, unique identifiers that are universally known and accepted for characters. UTF-8, UTF-16, these are binary encodings for those code points. So just keep those separate in your mind. So, let's talk layers of abstraction. Let's put this all in a little bit of context, right? On a high level, I'm going to use the computer. My clicker stopped working. On a high level, you deal with the display layer, right? You show characters on a screen, you print them. The stylized character is called a glyph. You render it using font rendering, etc. Below that, you have the text layer of abstraction. This deals with the elements of our written languages. This is what we as humans deal with, right? This is what Unicode and CodePoint tries to address. It gives unique IDs to those characters. But then ultimately, computers speak bytes. We need to store and transmit them. So we need something like UTF-8 to represent it in binary. Those are the layers you're going to have to deal with. How does Python deal with this? Well, specifically 2.7, because 3 is different, right? And you should go learn about that if you're going to use 3. But Python 2.7 gives you the string type, the str type. This is a byte string. It's a sequence of bytes that represent text. And what that implies is there's a specific character encoding there. There's no such thing as like plain text bytes. There's always a character encoding, and you need to know it. Python also gives you the Unicode type. This deals with code points. This deals with that text abstraction layer. So even though Python has an internal representation, when you're dealing with a Unicode object, you as the programmer don't need to worry about the encoding. This is characters. This is Unicode code points. So you're going to need to translate between your bytes, your byte strings, and your Unicode, and vice versa. How do you do that? Well, if you have some bytes, you need to turn them into Unicode. That's the decode operation. You're decoding your encoded bytes into Unicode. Going the other direction, you've got a Unicode object. You want to encode it into bytes so you can store it or transmit it. Well, it's the encode function, right? The encode operation. For beginners, sometimes keeping these straight and the directions is a little tricky. I came up with this mnemonic device I use in my head. I just misspell the function names. If I have bytes, I bcode them. If I have Unicode, I unicode them. I don't know if that's helpful for you, but I thought I'd throw it out there.
So the fundamental thing that you need to know about a byte string is that it contains no information in and of itself about how each sequence of bytes should be decoded back into the character. You have to be told via some sort of external declaration what encoding was used to store that text as a byte string. So you might find this in a document header, an HTTP header, or other file metadata, or even a code comment or an email from a coworker telling you what encoding was used. The point is, if you don't know what encoding was used on a given byte string, you can't figure it out just by looking at the string. You have to be told what encoding was used, or else you can't be sure that you're decoding properly back into the original text. So knowing these fundamentals, what can we as Python developers do to write applications to handle our text properly? Let's walk through a simple application that we're going to build right here. Let's say that we have this CSV file as our data source, and it contains a bunch of car reviews, because we're a car website. We're going to write a simple Python application to do some processing of the text and store that text in a Postgres database so that ultimately we can render it in a browser on a website like newcars.com. Let's take a look at our source file, the CSV file. You can see it was created using Microsoft Excel, and the person who sent us this file says they used a really old version of Windows. And so we're going to say that this was Windows 1252 encoded, or CP 1252 encoded. Our application is very simple. We're just going to look for instances of the word Montreal without any accents, and we're going to replace it with the word Montreal that's properly spelled with the accent over the E. When we store our text data in our database, we want to use Postgres, and we're going to use UTF-8 as the encoding that we want to convert our text into byte strings as, because it's a best practice. The reason for this being that we know that we can handle any character that comes across from our source data through our application if we use a target encoding that is Unicode aware. Taking a closer look at an example review, you can see we have the target word that we're going to replace with our application. I also want to point out a couple characters here, though. These don't lie inside of that A to Z 0 to 9 ASCII range. And so if we were ever to use an encoding other than our source encoding of CP1252, then we might end up with the risk of coming up with a different byte string representation for these characters. I'm just doing a little foreshadowing here.
So let's write some code. Just going to walk you through this line by line. This is our application. We're going to start off by declaring the encoding of our source code. You guys should be doing this. There's a number of reasons why, but basically you're telling potentially your text editor, but more importantly the Python interpreter, the bytes that are to follow should be interpreted as being such encoded. And so we're using UTF-8 for our encoding. We're going to open the file. We're going to iterate over it line by line, and we're going to do some very simple CSV processing. We're just going to split on the comma. And then we're going to do some simple text processing. We're going to call .replace on our review text. We're going to search for the Montreal spelt without the accent, and we're going to replace it with the properly accented version of Montreal. And then ultimately, we're going to store that in a database using this simple database API that we have at our disposal. Let's run this code and see what happens. So, okay, the code ran. Our data's in the database, but this is what we're seeing. We're looking at our UTF-8 encoded Postgres database, and we're seeing this. Not what we were hoping for, right? You've got the question mark lozenges in there. Something didn't go right. Montreal did get properly replaced, so we're happy about that, but we got to figure out what's the deal with these lozenges. So let's dig back into our code and try to figure it out. We're dealing with text. We're dealing with character encoding. We're dealing with byte strings. So I've highlighted all the byte strings here. And when we have a byte string, we know there's an encoding. What encoding do these byte strings use? Well, let's figure it out. We've got our string literals. We use the quotes. We create a string type in Python. The string literals are UTF-8 encoded. Why is that? Well, we declared our source code to be UTF-8 encoded. And so therefore, we also wrote bytes into that file that were UTF-8 byte strings, and Python interprets our string literals as those UTF-8 byte strings. Now we're reading CP1252 data out of this CSV file. So the data that we're reading out, the variables that we're assigning those byte strings, are CP1252 encoded byte strings. That leaves us with one byte string we haven't talked about, converted review. What character encoding is converted review? Well, we're creating converted review, and we're creating it with this operation. We're taking a CP1252 byte string, we're telling Python .replace, and we're handing .replace UTF-8 encoded byte strings. Python will happily do that for us because Python doesn't know about these encodings. Python's just looking at bytes in this case. So Python created a nice mixed encoding mess for us. Really, we created it by just telling Python to do what Python does. And then we stored that in our database. So visually, here's what happened, right? CP1252 source data coming out of our file. We tell Python .replace, here's UTF-8 byte string. Python happily operates on those bytes for us and gives us a byte string that contains some CP1252 bytes, some UTF-8 bytes. Now when we load that in our database client, the database client is looking for UTF-8 bytes because it's a UTF-8 database and we just connect to it using UTF-8. When the UTF-8 database sees these CP1252 curly quotes and euro symbol, it just throws its hands up and says, those are bytes I don't recognize, I can't interpret them as UTF-8, thus the question mark lozenge.
So what Travis has just illustrated is best practice 1 that we recommend, know your encodings. There's no such thing as a plain text string on a computer. The only way to store text on a computer is to encode it into bytes, and you have to know what encoding you're using to turn that text into bytes. So let's fix our application. We know we want to avoid mixing up encodings the way we just did. We should probably be dealing with Unicode characters so that we're dealing purely on the level of the text. So let's take those row text objects that we pull from our file. They're byte strings. Let's call decode on them to turn them into Unicode objects. Then we can split them into to get our author, date, and review text as Unicode objects as well. And we're also going to replace the byte string literals in our application with Unicode literals. So now we're dealing with Unicode at every level in our application, and we should be good to go. Oh no, except we're not. So you've probably seen this error message many times, some of you. What is the word ASCII doing in that error message? We never declared anything to be ASCII in our application. Let's take a look at the row that caused the exception in our code. So we called decode on this row text byte string, but we forgot something. We forgot to tell Python what encoding to use when decoding that byte string into a Unicode object. So Python 2 has some problematic default behavior. It tries to be helpful and assumes that you want to use your system's default encoding, which in most cases is going to be ASCII. And so when it encounters those curly quotes, ASCII is going to blow up and your application is going to fail. What we've actually done is a less than best practice known as Unicode whack-a-mole, which I'm sure many of you have played. We've played it plenty of times. And it's exacerbated by Python 2's problematic default behavior. The fix is pretty simple. You just have to explicitly declare the encoding that you want to use. In our case, this is CP1252, our source encoding. And so now that we've declared the encoding, Python can correctly turn that that byte string object into a Unicode object. I also want to point out that in the final line of our application, when we insert our data, we now have 3 Unicode objects that we're sending over to our database. Depending on the database that you use and the features it has or the API that you have at your disposal, this may or may not be a problem. In our case, we want to explicitly encode those Unicode objects into byte strings. And of course, we're going to declare the encoding that we want to use, which is UTF-8. So let's try running the application one more time. And finally, we get what we're looking for. Everything looks good.
So this is best practice number 2. Esther just walked you through it. It's called the Unicode sandwich. And it's not quite as delicious as it sounds, but it does make your life nice. So let's take a look at that, right? The Unicode sandwich is just this. You're going to decode from bytes early in your application. As soon as you're reading bytes out of a file or getting them across the wire, decode them into Unicode. Then in your application layer, you can deal with Unicode. You can deal with characters and not have to worry about character encoding. And then you're going to encode back into bytes late in your application before persisting or transmitting that data. So again, what did that look like in our application? Well, Esther decoded from CP1252 as she was reading bytes out of the file. And then she encoded into our target UTF-8 encoding immediately before persisting those bytes in the database. And what that allowed is everywhere in the middle, we had delicious blue Unicode ice cream filling, and we didn't have to worry about character encodings in our application. This really does make your life nice if your application will allow you to use this pattern.
The third best practice that we want to recommend is for you to write good tests against your code to make sure that it is handling text properly. You want to test the ranges and boundaries of the encoding that you're using. If your application is supposed to handle Unicode text, then be sure that you're using test strings that contain more than just the A to Z, 0 to 9 ASCII range. There are fancy text generators online that you can use to generate some crazy Unicode characters that you can put in your tests. You also want to test your interfaces against both Python Unicode literals and byte string literals. You may be using libraries in your application that do their own Unicode to string conversions, and they may or may not do it correctly. You can't be sure unless you write tests. So if you have something that expects Unicode, throw it a byte string and see what it does. And if it expects bytes, throw it a Unicode string and see what happens. You want to make sure that your text isn't causing problems as it makes its way through your application. And you also want to test for the handling of incorrectly encoded text. If you have code that expects ASCII, try throwing it some UTF-8 encoded text and see what happens. Maybe you want to raise an error right away so that you know that you have a problem in your source data that's changed. You can call the authorities, complain, whatever. Or maybe you want your application to chug along without breaking. Whatever you do, make sure that you are writing the proper tests for this.
So just to recap those best practices for you. Always know your encodings, because there's no such thing as plain text, right? If you have bytes, they're encoded. You need to know what encoding was used. Then wherever you can, use the Unicode sandwich so that you can deal with text with Unicode in your application layer and you don't have to worry about encodings. And then finally, test your code. I hope this is a best practice you all see the value in Python in general. But when you're talking about text and character encoding, these bugs are sneaky, right? Because your application is working and then all of a sudden you encounter a character that comes across an API or in a file and your application blows up. So test your text-related code. So we know our best practices. We're using them. Our world is great. We're doing the right thing. But ultimately, your system is going to interact with outside systems, outside external data, and someone else's system is going to cause you pain. So what does that look like? What can you do about it? A couple quick examples. What happens when you get a file that is using an incorrect encoding, or an encoding that's different than what was declared? So example of that, we have our application. It's processing our CP1252 data day after day, month after month, year after year. We're happy, we're enjoying life, and then one day, UTF-8 shows up. And we don't know about it, right? This was still declared CP1252 via the water cooler conversation with the coworker 2 years ago when he told us he was going to email us CP1252. But one day we get UTF-8, and we run our program, and nuclear table flip, it blows up, and we're not happy. So how do you deal with this? Well, this is a pretty simple one, right? There's human interaction. You can go talk to people. You can use your words. You can ask him, what happened? What happened to CP1252? Why did I get UTF-8? Did you get a new program? What's going on? But maybe he left the company, or maybe you're not on speaking terms, or maybe he's up in management and won't talk to you about character encoding anymore. And in that case, you're going to have to guess. And you can just blindly guess. You can say, ASCII, UTF-8, let's try it and find out. But that's not a great way to write quality software. So you can guess intelligently by using a library like Chardet, and Chardet is just going to look at your bytes and give you statistical probability on those bytes, meaning it was encoded in a certain encoding. So, this is 90% chance this is UTF-8. But ultimately, that is a guess based on probability. Maybe someone invents a new character encoding and Chardet doesn't know about it yet, or something like that. Just understand it's a guess. And then, again, if you wrote your tests, you already know how your application is going to fail in this case, and presumably you wrote it in a way where you aren't going to have to flip tables when you encounter UTF-8 data.
Another problem that you might encounter is, what if you receive data from an application developer who didn't watch our talk? They played a little too much Unicode whack-a-mole. So they give you these strings in your source data that are all mixed up. They contain garbage characters, misencoded, misdecoded characters, mixed encodings, or just escape characters. There's a word for this. It's called mojibake. And it's a real pain to fix because, first of all, you don't know what that developer did to give you this mixed up string and how they misencoded and mixed up those encodings in their text, much less how are you supposed to know what the original characters were supposed to be. To use one example that we've encountered, this here is supposed to be the name of a car dealer, and you can tell it's not quite correct. How did it get this way? We're going to play a little Unicode CSI here. We're going to encode that Unicode string into a byte string using our known encoding of CP1252. And we're going to end up with this byte string sequence. So you can see here each character up above is color mapped to the byte string representation of it below. We did some extensive research on this sequence of bytes. And we found that in a different encoding, those three characters, those three bytes actually, represent a single character using UTF-8. So just to clarify, you have this byte string with those three characters, those byte strings sequences, that if you decode using UTF-8, will actually give you a much more reasonable looking name for an auto dealer. To recap, somebody had a smart apostrophe, basically, that they encoded using UTF-8 into the following bytes. And then somebody else, or maybe even the same person, misdecoded it using the wrong encoding and gave us these three garbage characters. And so this is how mojibake is born. And there are a couple ways to fix it. Actually, one thing you can't do is to change the encoding that you're using to UTF-8 because you know that the rest of your source data is CP1252. So what you could do is maybe keep track of known troublesome byte sequences like the ones that we have here, and just kind of keep track of them and do a manual replacement with the byte string representation that's correct in CP1252 for that character. If you do this, so your list is only going to grow the longer your application runs. It's a huge pain to maintain. Luckily for you, there is a library called Python FTFY, fixes text for you, and it fixes mojibake. So it has its own conversion tables and uses heuristics to process text and try to clean up any mojibake strings that you have. All you have to do is pass it that mojibake Unicode object, run fixed text on it, and it'll throw you back its best guess for what the cleaned up, more correct string should be. It's not a perfect library. It's still under active development, but it's really good. We use it in our production code. It saved us a great deal of time.
So one more issue, and that's where you need to store data using a target encoding that can't handle the characters in your source encoding. So what do I mean by that? Let's say you have some source data that's UTF-8, right? It's coming from Twitter or something, and there's snowmen in there. People like to write about snowmen. And you're told you need to store this data in a CP1252 database, maybe it's MySQL, and that target database is out of your control. You can't change the encoding. You're told you need to store this data in CP1252. Well, the problem is CP1252 can't handle snowmen, short of some kind of crazy hack, which is not advised. So at the application level, what are your options? Well, the default behavior when you see a snowman or another character and you encode it into an encoding that can't handle that character is the strict behavior. And what Python does using the strict behavior is it just raises a stack trace, right? It errors out. So you could use this and write some fancy code that fires off an email and says, hey, we found snowmen in the source data. We can't handle this. Fix your source data or whatever. But that's not super flexible. So Python gives you other options. You have other options in any character encoding processing. So one option is to ignore those characters, right? You're processing your data, moving it to CP1252, and you just say, when I see a snowman, move along, everything's great here, just ignore it. But the problem is then your target data is missing those characters, and you might end up with some really funky looking output data. So a slightly more graceful way to handle it is to replace those characters with a surrogate character or just a placeholder. So you're processing your text, you see snowman, you say, I can't do snowman in CP1252, but I'm going to drop a marker here so the person who comes after me recognizes there was a character there that couldn't be properly encoded using the target encoding. It's important with both an ignore or a replace operation to note that these are lossy operations. That's obvious, but if you may be able to upgrade your database to UTF-8 in the future, then maybe it's worth keeping the source data around so that you can properly encode it in the future.
So with that, we've sort of run out of time, and we've come to the end of our talk. We hope that we've covered the basics well enough for you to do more research, but also to make your life a little easier even now. We want to thank the following people for helping us with our talk. And I don't know how much time we have left for questions, but we do have our slides up online right now. So I'm just going to blow through these. You can look them up yourselves and do some further reading. But our slides are up, and feel free to contact us through these channels if you have any questions. So thank you very much. Okay. I guess we have time for like one question. Okay. We can't hear you.
Yeah, Python 3. So Python 3 kind of flips everything upside down a little bit and reverses the roles, right? And we don't have enough time to give you any kind of actual grasp on that. Again, Ned's 2012 talk actually deals with it pretty well and explains it. There's some other talks. Go to PyVideo and look for the Unicode talks, and it will give you a good understanding of Python 3. Yep. Byte order marks, right. So some encodings, UTF-16, for example, will drop a byte at the very beginning of all of the text to tell you big endian, little endian. And so I don't actually, can't go super into detail on that right now. Again, there's some other talks that do get into the details on it. And frankly, I've avoided encodings where that was an issue, but I know it used to be a real big issue when kind of UTF-16 was the de facto Unicode encoding. So
yeah, what's nice about UTF-8 is that it doesn't require that byte order mark because it uses, it doesn't need those.
Yep. From future import Unicode literals, we haven't actually used that. I think, yeah, I better not speak out of turn. I've read about it a little bit, but the stuff we've been doing recently has been not required that. So, yep. Great, thank you.